Section 9, Friedmann acceleration equation and equations of state. Friedmann's first equation is not enough because we don't know how the energy density on the right-hand side varies with time or with scale factor. Friedmann assumed the universe is filled with a perfect fluid and assumed the validity of the first law of thermodynamics, with no heat transfer across incremental regions of the universe. You might remember learning that energy is neither created nor destroyed, but this is not what the first law says. Conservation of mass energy applies to an isolated system, but no region of the expanding universe can be considered isolated from the rest of the expanding universe. The entire universe expands together. We have seen that photon energy decreases with expansion. We will see later that total dark energy increases as volume increases. Friedmann got this fluid equation, where P is pressure. Epsilon is energy density. It may be surprising to you that the dimensions of energy density and pressure are the same. Joules per cubic meter is the same as newtons per square meter. So, adding the quantities is fine, though it looks unexpected. Taking the derivative of his first equation and using the fluid equation, we get Friedmann's second equation, the acceleration equation. The acceleration of the scale factor, A double dot, is on the left-hand side. Notice that the left-hand side is not squared. The first term on the right-hand side, in blue, is the negative of the total energy density of matter and radiation, for example, light, in the universe, plus 3 times the pressure of matter and radiation. This energy and pressure are always positive, so the acceleration due to this term is always negative. Because of this negative sign, matter and radiation cause the scale factor to decelerate due to gravitational attraction. This first term, the energy density and pressure of matter and radiation, cause the expansion of the universe to decelerate, slow down, for the first 7.6 billion years. It may seem confusing that positive pressure increases deceleration, but positive pressure decreases energy density as work is done by expansion. I explained this in supplemental video number 3. As the universe expands, the energy density and pressure of matter and radiation decrease with expansion, and this first term eventually no longer dominates this equation. The second term on the right-hand side, in green, is the cosmological constant, or dark energy term, which is positive, not zero. About 6.1 billion years ago, the matter and radiation energy density and pressure fell to the point that the dark energy density has dominated this equation, and the expansion of the universe changed from decelerating to accelerating, because the blue term is negative and the green term is positive. Later we will look at possible ways our universe might end. There is no curvature term on the right-hand side of the acceleration equation. You might remember that the pressure of a gas of atoms or molecules can be calculated from the ideal gas law equation. This is called an equation of state, but for cosmology, the situation is even easier. For matter, pressures since the first second after the Big Bang have been insignificant compared to rest mass energy density. So the pressure of matter, subscript m, is 0 to cosmologists. The pressure of radiation, subscript r, is 1/3 the energy density of radiation. The cosmological constant can be re-expressed as an energy density and a pressure, and can be extended to a dark energy whose energy density need not be constant. When we do this, we get that the pressure for dark energy, shown with subscript capital lambda, equals W times the energy density of dark energy, where W is close to -1, and is exactly -1 if the dark energy density is forever constant. The energy density of dark energy is positive, but the pressure is negative. It is the negative pressure of dark energy that causes expansion to accelerate. At first, encountering a pressure that is negative is unexpected and seems wrong or ridiculous. In order to keep going on expansion of the universe, I moved the explanation of negative pressure to supplemental video number 3. But if you cannot wait, it is a little similar to the restoring force of pulling a spring to a longer length, but with a constant force.